Hey guys, I'm going to go over our study guide for Fnet equals 0 with you if you need a little bit extra help with this. So the first page of this is going to have a lot of just free body diagrams. So you're going to have a box and you're going to have to draw the forces that are acting on it. You want the back of the arrow to start on whatever object it is and the arrow to point in the direction of that force. You also want to label that force. So the first one is a ball in projectile motion. No matter where this ball is in projectile motion, whether it be here, or here, or here, the only force on it would be weight, which we could also write as mg. The second one is the ball that is falling in terminal velocity. So terminal velocity is going to be when an object is falling and the air resistance up is balanced by the weight down. And I could designate air resistance as a lowercase f. You don't want it to be a capital F, but it can be a lowercase f because it is a kind of friction, and these are equal. So this would be B. C, a ball in free fall. Something in free fall is falling only under the effects of gravity. So this is just going to be a straight arrow down for gravity. D, a sign hung with two wires at an angle. So the direction of force in a wire can only be in the direction of the wire. We call this acting axially. And we would say that this string is pulling in its direction, that string's pulling in that direction. Because the angles aren't the same, I'm going to differentiate them. I'm going to call one T1 and one T2. And then I have weight going straight down. In E, we have a block just being suspended by a wire. You're just going to have a tension up and a weight down. Those would be equal. F would be a ball being pulled up by a wire and it's accelerating. So in that case, I would expect my tension up to be longer than my weight down. And again, it could be W or mg. You don't have to do both of them. G, a book at rest on an incline. One of the last things we did was the incline lab. In this case, you should have the weight going straight down. You should have the normal acting perpendicular. And you should have friction in the direction of up the incline. So friction is always going to oppose the direction that something is sliding or the direction that it wants to slide. So a block's natural intention on a hill, on an incline, would be to slide down, so we have a friction that is directed up. And then we have H, a book sliding down an incline with no friction. So that's going to be the same as what G was, except now there's no friction. So even though it's sliding down, there's no arrow pointing down. So these arrows don't describe how something's moving. They describe how the forces are acting on it, which will tell us how it's going to accelerate as time goes on. All right, terms to know. And we'll go over this in a Kahoot. We need to know Newton's first law. We need to know what inertia is. We need to know what mass is. We need to know what weight is. We need to know what mu is. We need to know what friction is, tension is, normal force, mg, equilibrium, constant speed, constant velocity, acceleration, and Fnet equals 0. So we'll go over all of those in the Kahoot. But on our test, we do have conceptual questions. There's 4 math problems, there's 10 FBDs, there are 5 conceptual questions. So I'm going to go on to number 3. A horizontal force of 10 newtons pulls a 50 newton box sideways at a constant speed. So for these, you're going to also have to have a free body diagram. So we're going to have a weight going down and a normal going up, and we're saying that it's being pulled just sideways. If it's at constant speed in a straight line, that's a case of equilibrium. That's a case of balanced forces. So that means something has to balance this arrow that's going to the right. And that would be an equal arrow going to the left. And in this case, that balance is going to be friction. All right, so I know that this is 10, and I know that this is 50. And so if I want to find out what mu is, mu, and this would be kinetic mu, because it is sliding, is equal to my friction divided by my normal. So I'm going to be able to find each one of these with Fnet equals 0. So in the x direction, Fnet is equal to 0. This is in equilibrium. This is in equilibrium because it's moving with a constant velocity. It's not changing direction nor changing speed. So I'm going to take my forces to the right minus my forces to the left. This is the convention in math. We take things that go to the right and up to be positive when we're graphing. So I'm going to have T minus F is equal to 0. So my tension is equal to my friction, which is 10 newtons. In the y direction, I'm also going to have Fnet equals 0. And I'm going to take up minus down. So this is going to be normal minus weight equals 0. It's really easy when there's only 4 arrows and you're balancing them. So my normal is equal to my weight, and this is equal to 50. So my mu, which is F over N, is just going to be 10 divided by 50, which is 0.2. So this doesn't have any units. This is a ratio, very much like pi and radians, which are also ratios of 2 of the same things. So the top and the bottom of our fraction both have newtons, and they both cancel out. So this was the case that we saw in the first example problem in the notes, also in the first and third ones you did in the friction lab. Let's move on to number 4, which is going to be like the second one we did in the friction lab. So this one's a little more complicated because you're pulling at an angle. And when you pull at an angle, your tension does multiple things. It exerts a force both in the x direction and in the y direction. And we're going to have to resolve those separately, which means break them into components and consider just what's going on in the x direction and what's going on in the y direction. So again, we have a box that is being pulled, and now I'm saying that it is being pulled at an angle of 30 degrees. Normally, something on level ground, we'd measure the angle from horizontal, where horizontal would be 0, and as we go up, it would gain, going up towards 90. It's going at a constant speed, so that means that there needs to be a force of friction that's balancing out the x component of the tension, and it's also going to have a weight and a normal. And these aren't going to be equal. because there's an extra force that's acting in the y direction, and that's going to be part of the tension. So part of the tension is actually acting in the y direction. So what I need to do, our first step is the free body diagram, and you're going to get points for drawing each one of these arrows and labeling them correctly. The second thing we need to do is make sure our calculators are in degrees and redraw this arrow off of the free body diagram. And I want to resolve it into its components. So I'm saying that t is going to the right and up. I could replace it with an arrow that just went to the right and one that just went up, which is going to be tx and ty. Now I want to write these in terms of t. I don't want to just leave them as tx and ty. Why? Because tx and ty aren't real. They're made up to help us solve this problem. So if I can explain them in terms of t, maybe I can solve for something else in our problem. So this is our adjacent side, tx. So according to SOHCAHTOA, I would use cosine. So I'm going to say that cosine of 30 is equal to my adjacent over my hypotenuse, and that's going to be tx over t. So tx is going to be t times the cosine of 30. And we're saying that t is 10 newtons. So this is going to be 8.7 newtons. So we're saying that we're pulling with a force of 10 newtons right here. I'm going to do the same thing with the y component. So with the y component, this is the opposite side, and I know that the sine of 30 is equal to opposite over hypotenuse, and I have ty over t, opposite side over hypotenuse. So I'm going to multiply by t. I'm going to get t sine of 30. So this is going to be 10 newtons sine of 30, which is 5 newtons. So this pulling at an angle at 10 is pulling 8.7 sideways and 5 up, which is going to change the normal. It's going to make this box a little bit easier for the ground to push up on because my pulling is pulling up on it a little bit. All right, so let's look at our x direction because that's the simpler one. So in the x direction, I'm going to say that Fnet equals 0. All this means is that our forces are balanced. How do I know that my forces are balanced? Because they're telling us it's getting pulled sideways with the constant speed. If there was an extra force, it would be a changing speed. It would be accelerating. And so I'm going to take the forces that are directed just to the right minus the ones to the left. So going to the right, I have Tx. Going to the left, I have friction. So we're saying that this is 8.7. So my friction is 8.7 newtons. The y direction is a little bit more complicated because we have 3 arrows. I have the normal going up, but I also have part of t, and then I have w going down. But they're also still balanced. Where this is sliding sideways at a constant velocity, up and down, nothing's happening. It's Fnet equals 0. They're balanced. So we're going to say that in the y direction, Fnet equals 0. I'm going to take up minus down, but I'm going to have 2 up. So maybe I should have wrote ups. So this is going to be n plus ty minus w is equal to 0. And every time I say ty, I want to say ty Hilton. All right, so I'm going to subtract ty and add w to both sides. Or if you want to, you could put in the numbers. I'll do it both ways for you guys. But I like to put everything on one side and then substitute in the numbers. So on this side, I'm going to have n. And on this side, I'm going to have w minus ty. And they give us what our weight is. They changed the box to 30 newtons. So this is going to be 30 newtons minus 5 newtons, and this is going to be 25 newtons. If you want to put in the numbers right away, we know this is 5, we know this is 30. So I'm getting that N is equal to 25. The last part of this is they ask us to solve for mu. So since it's sliding, it's the equal to, and mu is the ratio of how hard is it to drag something compared to how hard is it to lift something. And so in this case, our force of friction is 8.7. Our normal is 25. And according to my key, I have 0.35, which is probably pretty close to what we got in the friction lab. So the first two questions go along with the first 3 problems we did in the notes, and then the 4 problems from the friction lab. All right, let's move on to number 5. This is going to be the incline. We did this most recently as a lab. So most recently as a lab, I had you guys balance a dynamic track with 1 fishing weight, then 2 fishing weights, then 3 fishing weights. And we balanced it out. We solved for our tension. We drew free body diagrams. We rotated things. We resolved our components. And we solved for what the angle was, and actually even calculated what our percent error was. On the test, it's going to be a little bit simpler. But this would be like the example from the notes we did. We did a few in the notes, and then you guys did 3 on the lab. So a 20 Newton box is at rest on a 30-degree incline. So when they tell us what the angle is, it's always this lower angle of the triangle. And this goes for real life too. So if you're talking about a road, they would say that this road has a 0-degree angle, has a grade of 0. And then as it goes up, we're measuring what this angle is with a horizontal line going up. So on our free body diagram, again, arrows starting on the object and going away, we're going to have weight going down, normal going up. So perpendicular, a surface can only push perpendicular, and then friction is opposing the motion down the incline. And I also know that it's a 20 Newton box. So I want to find the normal and the friction. So weight is equal to 20 newtons. The rule with this, and I know it seems weird, but we have 2 things at an angle and 1 thing that's not. It's so much easier to just have 1 thing at an angle than the 2 things at the angle. And plus, we know W, so it'd be good if that was our hypotenuse, because it'd be easy for us to find the 2 sides. So what you should do is pick up your free body diagram, take it off of your page, spin it, and put it back down. And when we do, the normal is going to go straight up, the friction is going to go to the right, and now it's only our weight that's at an angle. Now that I did this, this is no longer a free body diagram. So a free body diagram identifies the forces on an object, but it also tells me their magnitude, how long the arrows are, and also how they're pointed. And I changed how these are pointed. But I know that this angle is this angle. All right, so I'm going to solve for these 2 components, which I'm going to call Wx and Wy, with 30 degrees being up there in the angle. So our opposite side is going to be WX. So I'm going to say that the sine of 30 degrees equals opposite over hypotenuse. So this is going to be WX over W. I know what W is. It is 20. So WX is going to be equal to 20 times the sine of 30, which is 10 newtons. And you can probably tell already that that's what friction's equal to, because those two arrows have to balance because this isn't moving. I'm also going to do WY, and this is our adjacent side, so I'm going to use cosine. So cosine of 30 is adjacent over hypotenuse, and so this is going to be WY over 20. So WY is going to be 20 cosine 30, which is 17.3. Yeah. Now I'm just going to do the equilibrium for our two directions. And what we do is, with our axis, we make this what our axis looks like. So when we rotate it, it straightens out. I'm going to say that perpendicular to the incline, our forces are balanced. It's not moving. So I have normal minus WY equals 0. WY we said was 17.3. Parallel to the incline, or down the incline, Fnet is equal to 0. I'm going to take my rights minus my lefts. So I'm going to have friction minus WX is equal to 0. Friction is equal to WX, and we said that was 10. And that's our answer for that one. All right, our last example is something hanging. So we did a number of examples like this, both in the notes and we did it in the lab. We used a spring scale, which tells us what the force is. You guys are doing, you've done a gizmo as well on spring constants and springs, which is another example of equilibrium. So we held the mass up, we got what the force was, we suspended it by two different wires and looked at what those tensions were and calculated the components. On the test, we're only going to do one that is has one wire sideways, horizontally, and one at an angle. And so we have a sine. One force is sideways, the other one is pulling at 60 degrees. And they give us what this is. This is 100 Newton sine. Which would be about 10 kilograms, right? Because they could give you newtons or give you kilograms. All right, so I'm going to draw the forces that are acting on this sine, starting with the arrows on the sine and going in the direction of the force with the appropriate magnitude. So I'm going to have the weight going straight down. I'm going to have this tension, which I'll call T1, going in the direction of the arrow, acting axially. And then I'm going to have this tension acting in the direction of that wire. And those are our three. Now, one's at an angle. I need to get rid of it. I need to resolve it. We call that resolving. So I'm going to redraw my T1. And T1, the way I drew it, and in the picture it doesn't tell you, but on the test I'll give you a diagram so that you'll know which way to draw it. T1 is pulling, in my picture, to the right and up. So I can replace it with an arrow just going to the right and just going up. So I'm going to solve for what those are, and then I'm hopefully, knowing that it's 100 newtons weight, I can find out what my two tensions are. All right, so T1x, this is my adjacent side. So I would say that cosine of 60 is equal to adjacent over hypotenuse. This is going to be T1x over T1. Unfortunately, I don't know what T1 is. Up to this point, we did components. We knew what it was. We could put the number in and get a number. I can't do that here. But I can write that T1x is equal to T1 cosine 60. This is helpful. This is useful to us because we wrote this component that's made up in terms of something that is real. I'm going to do the same thing with the opposite side, T1y. And I'm going to say that the sine of 60 is going to be T1y over T1 because that's opposite over hypotenuse in our SOHCAHTOA. So I'm going to resolve this as well. I'm going to get it in terms of T1 and I get T1 is equal to T1y is equal to T1 sine of 60. Now you need to ask yourself, do I know anything about the x and y direction besides that they're in equilibrium? And the one thing that we know is weight. So I'm going to look at the y direction first because I have some information in that direction. So I'm going to say that in the y direction, Fnet is equal to 0. It's in equilibrium. It's balanced. These forces are balanced. So I'm going to take my force up minus my force down. So going up is T1y, but I'm going to write it as T1 sine of 60 because T1y really doesn't mean anything. Then going down, I have W, which I know is 100. So I can, if I want to put the numbers in right away, I could write T1 sine of 60 minus 100. So I'm going to add W to the other side and add 100 to the other side. And I'm going to get that T1 sine of 60 is equal to W, or T1 sine of 60 is equal to 100. And then I need to divide by sine of 60. And sine of 60 is just some decimal. It's 0.866. Right? It's radical 3 over 2, if you remember that from math class. So this is going to be 100 divided by the sine of 60. I would get the same thing over here. So this is good. This is useful information. Now I know T1. And 100 divided by sine of 60, I cannot do in my head. Making sure my calculator is in degrees, I got 115.5. 0.47. We're not building a watch here. So now I know this is 100, and I know this is 115. That's good. So this is 115. Because in the x direction, part of T1 is balancing T2. So now I can get T2 easily. And so I'm going to make a little bit of space for myself here. And I'm going to say in the x direction, Fnet equals 0. I'm going to take the forces to the right minus the forces to the left. So I'm going to have T1x, which I'm going to write as T1 cosine 60. Minus T2 is equal to 0. So T2 is going to be equal to T1 cosine 60. And I already said that this was 115. So putting this in my calculator, I got 57.5. If you put 115.47, you're going to get something close. I would accept either answer. So we're not as specific in physics as we are in chemistry, as they are in chemistry with significant figures. All right, guys. Good luck on the exam.